Welcome back to Chemistry 4300. In this video, we're going to review material in Chapter 2, which involves probability distributions. Now let's say you're in the lab and you have a sample in a constant temperature bath, and you'd like to know that that bath is doing a good job of holding the temperature constant. So you go in and you do measurements of the temperature, and you find that over time that the temperature is not exactly constant. It seems to be fluctuating a bit. But generally you see that it's about 31.1, but there's fluctuations on the order of about 0.2 degrees during that measurement. Now, if you wanted to report that to others or write it into your lab book, one thing you could just write down was the mean temperature was 31.1. But if you wanted to capture this variation, this width here that was taking place during the measurements, then you could do what's called a histogram of all the measured values. And the way you do that is that for a given temperature, you make a bin width centered on a given temperature, and any time a temperature falls in that bin width of temperatures, then you add to the count, and then you plot the count as a function of all those bin centers, and this gives you what's called a histogram. Now, in this case, we did 128 measurements, and this is what the histogram looks like, and you can see the value is about 31.1, and it has a width of about 0.2 degrees. Now let's say other colleagues of yours go into the lab and they make measurements on the same sample in the same bath. And say two other colleagues, so this is you and two other colleagues that are doing the measurements. All three of you did 128 measurements, and when you made your histograms, you can see that the values are still about 31.1 in all three cases, but looking closely at the histograms, you can see that they're not exactly the same. And that's not surprising, considering random variations in one scientist's measurement are going to be different than the random variations in another scientist's measurements. So it's not surprising that they're different here. But one thing you'll notice is that, let's say all three of you went back to the lab and you did 1024 measurements. Well, you'll still see that your distributions are fairly similar and that there are some variations, but the variations here are not as great as the variations here in the 128 case. So let's say you went back to the lab and you did 4,096. Well, again, the histograms look fairly similar, and now the variations are even less than they were in the 1024 case, and even more less than they were in the 128 case. So you can see the pattern here, and as you continue to do more and more measurements, in the limit that you do an infinite number of measurements, those histograms from the three different scientists would be absolutely identical. Now, an infinite number of measurements is not possible, but what we say mathematically is that in the limit that n goes to infinity, the histogram, or what we call the sample distribution, will become something called the parent distribution. And that parent distribution I've represented here with this green line here, that curve, in its sense, represents a histogram with infinitely narrow bins. That curve represents what's called the parent probability distribution. And that is what determines what these distributions look like for a finite number of measurements. Granted, there's some randomness that changes these with each measurement, but they're all governed by the same underlying parent probability distribution. Now, one of our main objectives in making a measurement is to determine what is that parent distribution that will be used to sort of predict the spread in the measured values. So this parent distribution, I'll call it P of x, is also what's called a probability density function. And a probability density function needs to be, one, positive for all values of x, and two, the area under that distribution needs to be unity. So if you integrate over all possible values of x, the integral should come out to be 1, meaning 100% certain that you're going to get a value that's in the range of all possible values of x. So let's look at an example of what could be a probability density function and see what we can learn. Now, the question I'm asking here is, can a function that's e to the minus x squared be a probability density function? And if not, can we scale it by some normalization factor to make it a valid probability density function? So what we're going to do first is we look at this function and we see, okay, clearly e to the minus x squared is going to be positive for all values of x, so it satisfies that constraint. But we can also then go look up, I'll say we'll use some integral tables. If you look this guy up in an integral table, you'll find that this guy integrated from minus infinity to infinity gives you a value of square root of pi. So clearly, the integral of this guy is not unity. So it can't serve as a probability density function because the area under the curve is not 1. However, it is a constant value, so we can simply scale the function by a constant value, and we will create a function that is a probability density function, because now the integral of this guy is going to be equal to 1, because we know the integral of this guy is pi, square root of pi over, and this guy divided by square root of pi means the integral is going to be 1. So this means that this p can serve as a probability density function. Now, it's important to remember that from the probability density function, you can get probabilities. So if I integrate the function between two limits, then that's going to give me a probability, which is effectively the area under the curve. So in this example here, between these two limits, 95% of the area is there. That means that that's what we call the 95% confidence limits. We're 95% confident that the value is going to fall between those two ranges. So these are what, as I said before, these are what are called confidence limits. And note the difference. I'm going to use uppercase when I'm talking about probability and lowercase when I'm talking about probability densities. Now, you have to be careful, because a probability density is not a probability until you integrate it between two limits. So by itself, P doesn't represent a probability, only a probability density. If you go into the lab and you make a set of measurements, you could calculate the mean by just adding up the measured values and dividing by the total number of measurements. That's the mean. In the limit that you have an infinite number of measurements, then that value that you get is what's called the true mean. But of course, practically speaking, you can't do that. So when you go into the lab, you make a finite number of measurements, and you do the same calculation, this time dividing by your finite number of measurements, n, and you get what we call the estimate for the mean. Only in the limit that n goes to infinity does the estimate of the mean become the true mean. So we'll use different symbols, mu for the true mean and x with a bar over it for the estimate for the mean. Now, if you knew the parent distribution that was governing this set of measurements, maybe you know it theoretically, for example, then you could calculate the true mean by just taking the integral of x times that parent distribution integrated over all values of x. That's how you get the true mean. And this is something we're going to be doing later in the class. We're going to be coming up with predicted probability density functions, and we want to know what the predicted mean value would be, and we'll calculate it this way. Now, sometimes when you're looking at distribution functions, you'll find that they're not symmetric, and so the mean might not be the best number you want to report, or maybe you want to report numbers to supplement the mean. And two other numbers that people often report are the median, which is the value that cuts the parent distribution in half. So if you integrate the parent distribution from one side to the median, then that will give you a value of 1/2. So what you're looking for is what this value is that gives you this value of 1/2. Another important one is the mode. So if you're just looking at the distribution, you're finding that where you have a maximum. So you take the derivative with respect to the measured value, say x, and you find out where you have a slope of 0, and of course where the second derivative is negative, meaning you have a maximum, and that over here would be the mode. Now, it's possible sometimes you'll have distributions that are multimodal. They may have 2 peaks or 3 peaks, and that's just the nature of the parent distribution. Now, another thing we're interested in is the variance, and of course the square root of the variance is the standard deviation, and the standard deviation is what we'll probably quote to people when we talk about what's the spread in the values in terms of how much they fluctuate randomly. So the variance you calculate by taking the values minus the true mean, square them, add them up, divided by n, and that gives you what we call the true variance. This is defined in the limit, again, of an infinite number of measurements. Now, the estimate for the variance is going to be done with a finite number of measurements, and you could calculate it this way, which is x minus the estimate for the mean squared, add them up, and divide by 1 over n minus 1. And the reason this is n minus 1 instead of n is because we've already used the data once to get the estimate for the mean. So that's 1 degree of freedom loss, so we have to subtract that from the total number of measurements. If, for example, you knew the true mean, but you didn't have the variance, then you could replace that with the true mean, and then you would divide by 1 over n. And as I just said before, taking the square root of these guys gives you the standard deviation, which is what people usually quote, look at for when they're trying to come up with ideas of what's the spread in the measured values. Now, if you have the parent distribution and you want to calculate the variance, then you would just calculate x minus the true mean, and you square that, and you would integrate that over all values. Okay, so that's it for this chapter. It's just a brief review of probability distributions and some of their properties that you need to be aware of.